Hi, everyone. I just wanted to just kind of wrap up our lesson on area between curves. I want to start with the example that we didn't get to on last week's notes, and then we'll look at a method to find the area of triangles using the ABC that we've been talking about, and I'll kind of show you two methods on how to do that. So the first example that I want to look at was the last example from last week's notes when we were integrating in terms of y. So the first thing that I'm going to do is I'm actually going to sketch these curves on my coordinate plane just to determine kind of what's what and what goes where. So in order to do that, I'm going to want to put things in terms of y, which it looks like the last three functions are in terms of y, but I need to make sure that this first function is also in terms of y. So just be careful with something like this. When you are getting this into a y equals, when you take the square root, don't forget that it's going to be the plus or minus the square root of negative x minus 2, which means that you're actually going to be graphing two separate parts here. That's really telling you that you're going to have a positive square root of negative x minus 2 and a negative square root of x minus 2. And you can definitely use your calculator to help you get some tables of values for those if you want to just kind of plug in values and see what works to do that. I think using the graphing calculator is a little bit quicker. So we'll graph those in a second. I'm just going to start off kind of with the easier functions here. So I'll graph the y is equal to x plus 1. And then I'll graph those two horizontal lines. Just going to put a couple of points in here. I know it's kind of hard to see on this coordinate plane. So there's my y is equal to x plus 1, and then I'll go ahead and sketch in the lines y is equal to 2 and y is equal to negative 2. Okay, so then I'm going to go and graph these two branches. So again, I'm just going to use my graphing calculator here to help me. If you want to graph these at the same time, you can. I'll just go ahead and do the positive first. So it looks like it's probably going to end up somewhere on this side of my coordinate plane. Looks like we're starting at the point negative 2, 0. I'll use the point negative 6, 2. And I'll use the point negative 3, 1. I missed that one. Okay, so there we go. So it looks like the branch is going to be kind of starting at this point and going upwards this way. And actually, you don't even need to go to your table of values to get the negative part of this, because what it's going to be doing is it's really going to be reflecting over the x-axis. So you're going to have some symmetry going on with the points that we just graphed. If you want to go to your tables of values, you definitely can. But I also know that if the point negative 3, 1 is included, the point negative 3, negative 1 is going to be included as the reflection. And then if the point negative 6, 2 is included, the point negative 6, negative 2 is going to be included. Because again, that's a reflected point. So my other branch is going to look something like this. And I know it's kind of hard to tell with this coordinate plane, but the area that I'm looking for should be in here. So I'm looking for the area contained in that region. And since we have a right and a left function kind of explicitly here, this linear function is our right function, then it looks like this function is going to be our left function. I would integrate in terms of y, which means that when we integrate in terms of y, we need to have all of our equations in terms of y. I'm sorry, in terms of x. So I want to solve for x with each one of these equations. So if I take y squared is equal to negative x minus 2, and I get this as an x equals equation, that's going to be y squared plus 2 is equal to negative x. And then if I divide everything by negative 1, that's going to give me x is equal to negative y squared minus 2. And then I also want to do the same thing for my linear. So my linear is y is equal to x plus 1. If I want to get this as an x equals, that's going to tell me that x is equal to y minus 1. And then this is my right function here because that's the linear. And then this is my left function here because that's really like that square root thing that's going on here. And this negative 2 and positive 2 are actually our bounds, because remember that when we're integrating in terms of y, we want to know what the lowest y value is and what the highest y value is. And those are our restrictions here telling us exactly what our lowest and highest y values are. So my setup for my integral is going to be from -2 to +2, bottom to top y values. And then I'm going to do my right function, so y minus 1, minus my left function, negative y squared minus 2 dy. If you want to clean that up a little bit, you definitely can. So that would be y minus 1 plus y squared plus 2 dy, which would really tell us we have the integral from -2 to 2 of y squared plus y plus 1 dy. And then at this point, I'm just going to use my calculator to evaluate what that area is going to be using my Math 9 option here. Oops. So -2 to 2. Again, I'm just going to type this in terms of x. And it looks like my area should be about 9 1/3 or 28/3. So the area or the area of that region is going to be about 28/3. All right, so moving on to something a little bit different. We know how to calculate areas of triangles from basic geometry, but we can also use calculus to actually calculate the areas. So what if I wanted to know the area of this triangle? There's a lot of different ways I can do that, but let's use the area between the two curves method. And what we're actually going to need to do for both methods that I'm going to be talking about, I'm going to be talking about using vertical rectangles and using horizontal rectangles, is we are actually going to have to split up our triangle depending on which method we're using. So for the first one, if I want to use a top function minus a bottom function, well, if I look at my graph, it's pretty clear that this line right here is always going to be our top function because it's always above my other two functions. So this one is always going to be our The problem is the bottom function is going to change. From our starting point over here on the y-axis, my bottom function is this up until this point. Because then over here, this actually ends up being my bottom function. So we kind of talked about that a little bit. What happens if we have something split where we have one top function in one place and a bottom function in another, and then something else changes? Well, we would just want to set up our integrals a little bit differently. We're going to have to split them up really. So the nice thing about this is we're given the vertices of the triangle and we know what our actual like function lines look like, but we need to know what their equations are. Well, if I know these points, so 0, 5, 5, 1, and 2, -2, these are actually just three linear functions that I can find the equations of. So my top function, if I know their points, I can figure out what the slope is. So my slope is going to be, let's say, 5 minus 1 over 0 minus 5. So -4/5. And I know what my y-intercept is. My y-intercept is going to be 5. So that would mean that this equation for this top function would be y is equal to -4/5 x plus 5. So top function, here's my equation. How about this equation here of this kind of like left side? Well, again, I've got 2 points, 0, 5, and 2, -2, so I can definitely calculate the slopes. So I'll say my slope is, let's do 5 plus 2 over 0 minus 2. So it looks like -7/2. And again, I know what my y-intercept is. My y-intercept is still 5. So the equation of this line would be y is equal to -7/2 x plus 5. And then I just have that other little piece here. Again, I can calculate its slope. So let's do, I don't know, 1 plus 2 over 5 minus 2, which is actually going to give me a 3/3. So it looks like my slope is going to be 1. And even though we don't know what the y-intercept is, there's a couple of different ways that we can figure it out. If I know that this slope is 1, I can actually just count down my slope to figure out what my y-intercept would be down here. or if you wanted to use an algebraic method to do that, you definitely could. But if I were to extend this line, it looks like my y-intercept would be 1, 2, 3, -4. So my equation of that line would be y is equal to x minus 4. So if I'm going to do top minus bottom, again, I know my top function is this. Let's start over here with this bottom function. So it looks like if I were to split up this triangle into a top minus bottom, here's my top, here's my bottom, and it would change right at this point. So if we're using top minus bottom, or if we're using vertical rectangles, we're going to be differentiating in terms of x. I'm not differentiating, I should say, taking the antiderivative in terms of x. So what I'm looking for in terms of my bounds are, well, what are the x values that we're going to be integrating from? So on this left side, my top function is going to be this y is equal to -4/5 x plus 5. My bottom function is going to be this -7/2 x plus 5. And I'm going to be going from the x value of 0 to the x value of 2, because that's the x values that this top minus bottom is covering. So 0 to 2 are my x values. My top is going to be -4/5 x plus 5 minus my bottom of -7/2 x plus 5 dx. And then my top versus bottom is going to be changing over here, because right at that x value of 2, now my top function is still the same, but my bottom function is now this kind of small little piece here. So my integral is now going to be, if I look at what x values this top versus, or top minus bottom is covering, it's covering the x values from 2 to 5. So I'm going to integrate from 2 to 5. Top function is still the -4/5 x function. But now my bottom function is this x minus 4. And if you wanted to clean this up, you definitely could. Maybe even just like distributing out the minus might be a little bit helpful when you're plugging in your calculator, just to make sure that you're not making any silly errors. You don't really need to combine too much here. So -4/5 x plus 5, and then minus x, and then plus 4 dx. And at this point, it's just a matter of using your calculator to evaluate. So I'll do 0 to 2. Oops. 0 to 2. And then I'll just put the -4/5 x plus 5 plus 7/2 x minus 5 dx. So it looks like this part here is 5.4. And then I'm going to do the same thing for my second piece. So from 2 to 5, do -4/5 x plus 5 minus x, and then plus 4 dx. So it looks like 8.1. So when I add those together, that looks like my total area is going to be 13.5. So using calculus, we're able to find out that that area is about 13.5. So what if I wanted to use horizontal rectangles instead? So what if I didn't want to do top minus bottom? So method 2 says, okay, well, what if I want to integrate in terms of y and I want to use maybe the right minus left? So this is going to be where I'm going to split up my triangle a little bit differently. The nice thing is that my equations are still going to be the same, so I'm going to go ahead and rewrite those. So my equation here is y is equal to -4/5 x plus 5. My equation here is y is equal to x minus 4. And my equation over here is y is equal to -7/2 x plus 5. So if I integrate in terms of right minus left function, again, it's going to be changing depending on where we're talking about within the triangle. So if I look at the right function, Well, here is the right function for kind of the top part of my triangle. Here's the left function for my entire triangle. If I look down here, this could be a right function, and then this would still be a left function. So it looks like where I'd want to split this triangle would be just about here. Because here's my right, up here, here's my left, but over here, here's my right, here's my left. And we know that if we're doing right minus left, we're going to have to integrate in terms of y, which means we're going to manipulate these equations in order to be an x equals equation instead of a y equals equation. So I'm going to go ahead and do that manipulation. So I'm going to get rid of the 5. So y minus 5 is going to be equal to negative 4/5 x. And then I'll multiply by the reciprocal. So x is going to be equal to negative 5/4 times the quantity of y minus 5. Over here, this one's pretty easy. X is going to be equal to y plus 4. And then over here, I'll get rid of the 5. So y minus 5 is going to be equal to negative 7/2 x. Multiply by the reciprocal. So x is going to be equal to negative 2/7 times the quantity of y minus 5. So now that that's in terms of an x equals equation, I can integrate with respect to y. So again, since I have split up my triangle, I am going to need to kind of think about what the bounds are going to be because there's going to be 2 different pieces to my integral. So what I'm going to do is I'm going to start with this kind of bottom piece here because that's going to be my lowest y value. So it looks like my lowest y value here is going to be a y value of negative 2. And I'm just going to go in terms of this small triangle over here. So this right minus left, if I kind of think about my cutoff point here, my y value of my cutoff point is going to be 1. So my right minus left of this function is going from the y value of negative 2 up to the y value of positive 1. And my right function is going to be this y plus 4. And my left function is going to be this quantity here, which I'm actually going to go ahead and distribute out as I'm kind of writing that in my parentheses. So negative 2/7 y plus 10/7 dy. So that takes care of this kind of bottom piece. And then my top piece, where now my right function is this one at the top and my left function is still the same one as my left function here, I need to figure out what my y values are going to be integrating in terms of. So it looks like the lowest y value in this triangle is going to be 1. The highest y value in that triangle is going to be 5. So I'm going from the y value of 1 up to the y value of 5. Here's my right function. So my right function, again, I'm going to distribute out as I'm writing this in. Negative 5/4 y plus 25/4. And then I'm going to go ahead and subtract out, again, my left function, which I've already distributed. So that's going to be the negative 2/7 y plus 10/7 dy. And again, we can clean this up a little bit before we plug it into the calculator. If you wanted to go ahead and go and evaluate as it is, you definitely can. So I'll write that as negative 2 to 1, y plus 4. I'll do plus 2/7 y and then minus 10/7 dy. And then my integral from 1 to 5, negative 5/4 y plus 25/4 plus 2/7 y minus 10/7 dy. And then again, I can just use my calculator to evaluate what those quantities are going to be. So I actually already did that workout, but you can, again, use your calculator to integrate those. Just make sure that you're plugging them in terms of x in your calculator. It'll still calculate the same area. So I believe this first quantity, when you do that, is like 5.7857. The second quantity is going to be 7.7143. And when you add those two together, you are actually going to end up with 13.5, which we know is our area that we got from using our vertical rectangles, which it should be the same, obviously, since it is the same triangle. So it does not matter which method you use. There is a practice problem like this one on the practice set that I'm giving you guys to work on tonight. So please let me know if you have questions, and good luck.